Let's say we have a container here filled with, I don't know, water or something. And we take a cube here. Cube means all sides are equal. They don't have to be a cube, but it makes the math in this case easier to see. And we have that cube that's floating in the water. Well, if it's floating in the water, we have a force in this direction called F1. We have a force in this direction called F2. If the thing is now moving, there's a force pushing, because we know the water is pushing on in this direction, and it's being canceled by that force in that direction. Otherwise, that thing will move side to side if it wasn't equal. Remember, we said early today, pressure equals force over area, which means what? Force equals pressure times area, P times A. Let's look at force 1. Force 1 pushing down must equal the pressure at that point, pressure 1, times the area. And if that's a cube, let's give it a dimension, length L, width L, height L. The area will be what? P times L squared. P, not rho. The pressure, pressure 1, let's call it pressure 1. That's the pressure from the top. Now, let's look at pressure 2 here. What is the pressure on the bottom of that? Pressure on the bottom is going to equal the pressure on the top, whatever P1, add to it what? Rho of the wood, the weight of the wood pushing down, if it's wood here, rho of the wood here, times gravity times the height, which is L. And we know F2, the force on the bottom, has to equal the pressure 2 times the area, which is pressure 2 times L squared. And we know pressure 2 equals pressure 1 plus rho times gravity times L, all of that times L squared. And what are we going to have? P1 L squared plus rho of the water here, or the wood, I'm sorry, times gravity. Let's go just rho here. Times gravity times L squared, that's L cubed. That's F2. And if you look at F2, F2 is going to equal to F1, this is F1 here, plus rho times gravity, times L squared, right? What's L times L squared? Which is the volume, right? That's the volume of that shape. So what's the difference between the two forces? It's rho times gravity times the volume. That's the difference between the two forces. Well, where is that force coming from? This is really the buoyancy force pushing upward. The water pushing up on you with the force of rho times gravity times volume. So F buoyancy is equal to rho times gravity times the volume. And that's the equation I was trying to derive there. Now, this actually only works, the buoyancy force only works, I'll wait till you finish writing. So the buoyancy says if an object is completely, that's the key word, object is completely immersed in fluid, doesn't have to be water, will experience or experiences an upward buoyant force equal to, or that's equal in magnitude. I want to say because force is a vector, the value of that vector, equal in magnitude to the weight of fluid displaced by the object. By the object. So, translation. If you have an object, here it doesn't matter what the shape of the object, immersed in liquid, your fluid. The fluid could be anything. This object has a force pushing upward on it called FB, buoyancy. And FB is equal to the weight of the object. But it says the weight, let's read that again. To the weight of the fluid displaced by the object. The weight of the fluid displaced by the object. Let's look at that statement. The weight of the fluid. Well, we know weight is what? Mass times gravity, isn't it? And to give the mass of an object, we know the density rho equals mass over volume. That means the mass equals density, that's rho here, times the volume. So the F buoyancy is equal to rho of the fluid, not the object, the fluid, times the volume, times gravity. And that's the buoyancy, actually, force, always pushing upward here. Archimedes came up with this actually calculation years and years ago because the king was given a crown. That's the story goes. And the king wanted to know if this crown was made out of gold or gold plated. So he asked Archimedes, which is a scientist, like was supposed to be a smart one, he said, I want you to tell me if this crown made out of gold or not. And Archimedes was thinking. They said in the middle of the night, he started running up and down the street naked. Eureka, Eureka, I found it. Your Majesty, I found it. I know how to find if it's gold or not. And what he came up with is we're going to put it in liquid, take a tank, and actually calculate what the buoyancy and all that, and based on that we can calculate what rho for that, and see if it's gold or not gold. And his research actually came up with the buoyancy force, bless you, equals rho fluid times V times G. Now, let's try some application on this subject. So this is really what buoyancy is. That's what section 4, just to come up with that equation. But I want to give you some application. I mentioned that, and that is to figure out body fat percent here, or we're going to take a person here, as I said, Springfield College here. If you want to know what is your body fat and all that, they take a tank, they put you in a chair, they know what the mass of the chair, they have a scale here on the top, there's color ropes hanging down, and you sit in this chair. Looks like you've been dangled in it, but you're sitting in the chair. Before you go in the water, you blow all the air out of you, and they dunk you in the water. Then, because this is full of water, the water is going to come off the side. They collect that water, measure the volume of it. So now, this person, before he got in the tank, has a weight of the person of 720 Newton, which means if we divide that by 9.8, that'll give me his mass, or her mass. So 720 divided by 9.8, this equivalent to about 73.5 kilogram. So this person has a weight of 720 in air, lowered into a tank full of water. So this is water. We know rho for water is roughly 1,000 kilogram per meter squared. Now, we have the scale sitting up there, and right before they dunk you, they put you almost up to your neck. If you ever done it, I had it done to me. You're sitting up to your neck, you're wearing like bicycle shorts, so there's really nothing taken, no volume, nothing. They prefer you go naked, but the lady did my test. I wasn't going naked there. She was my student. So I'm wearing bicycle pants, and right before, like up to my chin, I was there. She goes, okay, blow all the air out, Z. And I blow all the air out, then she dunked me in the water. The reason you blow the air out, because we want to know how much actually, what's your actual volume is. Because when you take a deep breath, what happened to your stomach? Expands, more water going to come out. So you blow the air out, exhale, then they dunk you in the water, in the tank there. So you completely submerge here. The scale is going to read a number on the top, and let's say the scale read on the top here 34.3 Newton. The scale says your weight here is 34.3 Newton. And the question, can you find two parts? Can you find the volume of the person? And part two, can you tell me what the density of the person? Now, if we do a free body diagram, this is you, that little dot represents you. What are the forces on you? We know we get your weight down, which is what? 720. We get the scale pulling up on you, and that's called the apparent weight. Remember we did in the lab there in the elevator? This is the apparent weight, WA. 34.3 Newton. What else we got? Excuse me. We got the buoyancy force pushing upward. These are the three forces on you. That's it. The first question, can you tell me what the volume of the person is? Well, we can calculate the volume there, or we can, from this picture, I don't even have to collect the water. I can look at the scale, tell you what the volume of the person. So if I didn't collect the water on the side here, which you don't have to, we can tell you what the volume of the person. How? If you're dangling there in that water, you're just not moving, because we have the scale holding you. We have static equilibrium, you're not moving. That means if you take all the forces in the y direction, they have to add up to a 0. Which means, translation, if you take all the forces pointing upward, they should equal all the forces pointing down. What is pointing upward?
The apparent force.
Okay. Apparent, where else?
And buoyancy.
And the buoyancy. And what's pointing down? The weight. So the 720 equals the 34.3 plus the F buoyancy, which is, remember, it's rho of the fluid. The fluid here happens to be what? Water times gravity times the volume. So I can move the 34 to that side. That will be what? 720 minus 34.3 is equal to 685.7 equals rho of water, which is 1,000, gravity, which is 9.8, times the volume. Can we get the volume of the person? That's the volume of the water that came out, which is your volume. We're replacing that by your volume. So the volume is 0.069, how about 0.7? It's 99070 cubic meter. Now this is question A. Question B, it says, what is rho of the person? What's your density? Well, we know density is equal what? Mass over the volume. Or weight, we can say the weight of the person equals the mass of the person times gravity. The weight of the person is 720 Newton here, not kilograms, 720 Newton. What's the mass? Isn't that rho of the person times the volume of it? Mass is, from this equation, rho equals mass over volume, which means mass equals rho times volume. Well, I know everything except rho now. Rho of the person. The volume, we just calculated that, 0.070. And gravity is what? 9.8. And we get rho of the person equals 1,050. Now, I don't know if I have a chart here to show you. If you want to get the body fat, by the way, there's an equation here. Ready for that equation? The book gives us that equation. They derived that for us. They want to know what percent the body fat is. Percent fat. So let's define X of F. X of F as body fat fraction. As a fraction. So you can multiply by 100% to make it a percentage there. But it's equal to, ready for this equation? 1 over rho of the person times ready for this? I'm going to put rho L, I'll tell you what that is, times rho F over rho L minus rho F minus rho F over rho L minus rho F. You want to take a guess what rho L and rho F are? Rho F is the density of fat. And rho L is the density of lean. We found out that rho F for fat, roughly, it's 9.0 times 10 to the second, or 900 approximately, kilogram per meter squared. And rho L for lean is approximately 1100 kilogram per meter squared. So you take the same two people, and one has more lean than fat, they're going to weigh more. You know, when people work out, so when you work out, you should really gain weight, not lose weight, because you convert the fat to a muscle, to a lean. Your density gets larger. So your shape might not change, and you might even gain weight. But you look at yourself, go, I look like I lost weight, but I didn't. But I weigh more, because you went from 900% body fat to 1100. So for this, if you plug in the numbers, where do we figure out the person body fat here? What was it? That example we just did there. 1050? So 1 over 1050 times, you're going to see this really, it's a number here. This number completely, if you do the math to it, this number becomes 4950 if you plug in these numbers into it. Minus, if you plug in these numbers into this, that's 4.50. Actually, I can make an equation look a little bit nicer. If I leave this person, rho for the person. So the equation actually for the body fat fraction is 4950 over rho per person minus 4.50. So that's really the equation you're going to be using. Where it came from? It came from that equation using these numbers. It becomes that. That doesn't change. The only thing changes rho for the person. So what's the for this example would be 4950. What was rho for that person? We said 1050. Do the math here. 4950 divided by 1050 minus 4.50. I came up with 0.214, which means percent body fat percent 21.4%. So once we know what's rho for the person is, we plug it into this one, and we have that number. Again, I don't have to measure how much water came out. I can calculate that. Or, if I'm not really good in math, I can measure the water comes out and use that equation to do that. When you measure something, when you collect it and pour it and all that, there's a chance of making a mistake. So it's really more accurate to do the math, calculate the volume this way, plug it in. Some people struggle with the math, so they go, you know what, I'll just measure the water. Once I know what V is, I know how much the person weighs, I can calculate what rho for the person is, go to this one, plug it in, give me that number, that's the percent body fat, with minimal understanding of physics. You don't have to be a physics major to figure this stuff, but that's where it came from. Let's take another example. This one is, see that in the ocean sometimes, you see a buoy there in the water, attached to a rope, attached to the ground. And if somebody comes in and cuts that rope, what will happen to that buoy? It will pop up in the air. So the reason it's not popping up in the air is because you get that rope pulling down on it. So let's see, we have here a piece of wood. So the buoy here made out of wood, this is wood. It has rho for wood to be 706 kilogram per meter squared. Tied with the string at the bottom of the water-filled tank here, whatever, or ocean, whatever you want it to be. The wood is completely immersed, completely. We'll get to partially immersed soon. And it has a volume of the wood to be 8.0 times 10 to the negative 6 cubic meter. And the question, the string is pulling down on you with the tension here. What is the tension by the string is equal to? Let's see, there's a free body diagram. That's the block of wood. What are the forces on it? We got the buoyancy pushing upward. What else we got? We get the string pulling down with the tension. What else we have? There's one more force. How about the weight? The weight of the block of wood is not pushing down. And the fact this is not going up or down, that tells me the net forces in the y direction has to be 0. Which means if you take the forces pointing upward, add them all, they should equal all the forces pointing down. What do we have pointing upward? F buoyancy. What do we have pointing down? The tension plus the weight of the wood. The buoyancy, remember, it's rho for the fluid, whatever the fluid is, times gravity times the volume. That's the equation for it. The tension is tension. The weight of the wood is the mass of the wood times gravity. The mass of the wood was not given to us. Well, what's the mass? Isn't that rho of the wood times the volume? Remember, rho equals mass over volume, which means mass equals rho times volume. So the mass of the wood is rho of the wood times the volume of the wood. Now we know everything. Was that put in salt water or fresh water? A piece of wood, density filled, water-filled flask here. So I'm assuming this is water from the faucet. That's rho equals 1,000. If it was an ocean, if it's a buoy in the ocean, the water is, rho for water, there's 1,030 for ocean, salt water. Unless you're the Dead Sea. And the Dead Sea much larger than 1,030. So rho for the fluid is going to be what? The fluid is 1,000. Gravity is 9.8. We know what the volume, 8 times 10 to the negative 6, equals the tension plus rho for wood, 706. Gravity, 9.8. The volume, which is what? 8 times 10 to the negative 6. Because if you put something that big in the water, that much water going to come out of it. How many unknowns? 1. And for this, if I did everything right, I got 1,000 Newton. That seems like a high number, right? Oh, let me try it again. That seems like a high number. Maybe I forgot the minus sign. E to the negative 6. Oh, what a difference. 0.023. Is that what you got? I got 0.0, I don't know how I come up with 1,000. 23 Newton. And that's the tension in the string. Hot air balloon works on the same logic. I'll explain that in a minute. But I also have a picture of the Dead Sea. About 20 years ago, we went to the Dead Sea. And I can tell you, see that lady reading there? That's not exaggeration. You will not sink. You will not. You just stand there straight up and you'll float. You're like a buoy. Very salty, salty water. Extremely salty. You do not want to shave and go there because you will scream the whole time. It burns like crazy. You can't open your eyes in the water. So you just, huh?
Is there fish?
Nope, that's what it calls the Dead Sea. Nothing grows there. I can tell you for a fact, I brought some water with me, but I had a rash on the side of my hip. And really went to about 10 doctors. Like, it didn't bother me. Just every once in a while I see the rash, I scratch it and all that. Since I've been to the Dead Sea, I've never seen that rash again. 20 years ago. Never seen it. Gone. Now actually there's fresh water leaking into it, seeping into it, and they say just a matter of time it's going to disappear. It's in Jordan. You know, that's where I grew up, in Jordan, so I went to it when I went to visit about 20 years ago. Took my kids, and people get the mud and they use it for mud bath, for healing and all that. So Israel and Jordan, they do have all these resorts on the side, and thousands of people go just for that. You take a mud bath, and suddenly, if you have any rash, the young age people have acne and all that, that's supposed to help with that too, you know. But let's look at the hot air balloon. You know, Now, if I have the density for the hot air balloon, for hot air, we'll use helium for it. We'll fill it with helium, because we know the density of helium. Somewhere, do I have hot air here with the density for hot? We'll use, you know what? Air is 1.28, we'll use helium, okay. When you heat actually the air, what you're doing is you lower the density of that, and that's why it rises. So, but I'm not sure by how much. I mean, I can make a number up there. You have and if you ever notice these hot air balloons, they are massive if you're next to them. I don't know if anyone ever been on them. I mean, that balloon is bigger than this room. So volume-wise, this room is probably what, 10 by 10, more than 10 meters by 10 meters. 10 by 10, let's say 10 by 10 by 10. The volume is 1,000 cubic meters, so it's really huge. And you have the fire going there, that's the heat. So the density now here of the air, the density of the air, normal air has a density, the surrounding air is 1.29. Well, by heating the air, it's going to expand. And the density of that is going to drop, let's say to 1, just for the sake of discussion. We'll use the hot air balloon H. But when you pull the balloon out in the basket, they have a weight to it. So the weight here is, so when you look at the hot air balloon, bless you, you get the weight of that. You get the buoyancy up there. And it's filled with air too. What about the weight of the air inside that, the hot air? WH, the weight of the hot air. The balloon you pull out of the truck there, your pickup truck, you open it, there's a basket, there's the plastic to make this when it's folded. You weigh it, it might be 200 kilogram. You know? The mass is 200 kilogram. Then you start putting air in it. Well, once you put it with air, that's the weight of the air too. You got to include that. That's part of the balloon now. Or you have people here. And your job to figure what's the maximum payload. How much more can you put there? So we also get the weight of the people. So if you want it to rise, you want that force to be just a hair bigger than this. If this is bigger than this, the thing rises. So by cranking the heat up here, you actually lower this value. You lower rho, and the hot air balloon start to rise. By lowering the temperature down, by not adding a lot of heat, this start to increase, and suddenly it's almost 1.29 and start to drop. The hot air balloon will start to come down. So by turning the torch on, you see the blowtorch there to heat it, the thing will rise, and anytime they want to come down, they just start to close a little bit there, just a little bit of hot air going up there, and the thing will come down slowly. If you want to stay just floating in the air, just floating right there, you got it to like over UMass, and now you're looking over Springfield, you want to stay at that height. Well, if you want to stay at that height, you want that force to equal the sum of these. The buoyancy is rho of the fluid. The fluid here happens to be, by blowing this one out, just think of it just like if it was water. If this wasn't water, when you blow it out, what happens? The water starts to drip down some into a container, we collect the water. Here we're pushing away what? The air. So the fluid of the air times the gravity times the volume. The weight of the people, which is, we'll leave it the weight of the people, we'll figure what that is. The weight of this has a mass of 200 kilogram, 200 times 9.8, plus What about the weight of the air inside the balloon right there? Which is the mass times gravity. Well, we don't know what the mass is, but we know it's rho for the hot air balloon times the volume times gravity. Mass times gravity of the hot air. Rho for air is 1.29, gravity 9.8. The volume, we say, is 1,000 here. I use 1,000 equals WP plus 90, yep, that's correct. 1960 plus 1 times 1,000 times 9.8. Hopefully that number is high enough, otherwise the thing might not rise. Let's see. $2,842 equals the weight of the person plus 1960, the weight of the people. So the weight of the people in this case is going to be 882 Newton, which means the mass 882 equals the mass times gravity, which is 9.8. The mass of the person, what? You can have only one person 90 pounds or less. I mean 90 kilogram, not pounds. 90 kilogram or less, which is about 200 pounds. So there's a couple of options to do. If you wanted to put more people, you better crank that temperature, lower that rho for H from 1 maybe to 0.8. If you can make it 0.8, you can take 2 people now. You can put helium. You can take 6 people probably with helium, if you fill with helium. Because helium rho for that is 0.179, 0.179, less than 0.2. So if I fill this with helium, I can take at least 5 people of 90 kilogram or more. Oh, I did all these in one step there, Mike. I multiply this, subtract them all, and I get that number. So I just did them in one step. The reason I do it in one step, I'll show you, I cheat in a way. I go, what is 1.29 minus the 1? These numbers are the same, you see them?
Yeah.
So I go 1.29 minus 1 is 0.29 times 9.8 times 1,000. That give me the difference between these two.
Oh, okay.
So that's why I do them that way. Now, sometimes when you put stuff in the water, it's not completely submerged in water or immersed in water. Sometimes just a portion of it. For example, if you take a cork on a bottle of wine or a champagne, you throw them in a bucket of water. Not the whole thing in the water, a portion of it. Or if you watch an iceberg floating down the river, not the full thing actually in water. You can see the seal sitting on top of it, and a portion of that ice is in the water, not all of it. So let's look at this when not the whole thing is submerged. Maybe I can come up with an equation. So let's take this problem. This is the water, and now what we have is a portion of that is submerged in water. some of it. So if I look at the piece from here, from the side, looking at it, this is what's submerged in water. This one in water. The rest is not. That's when the object is floating. See if I can find the equation. When you look at that floating here, why is it floating? Well, we have a force, a weight here, pushing down. We have something pushing up. We have the buoyancy pushing up, F buoyancy. We get the weight of the object pushing down. Let's look at the submerge. This is S for submerge. Maybe I'll use S for submerge. The weight of the submerge is rho of the submerged, that the block here, times the volume submerged times gravity. That's the portion of the block that's submerged in the water. It's the mass of that piece times gravity. Well, the mass is rho of the submerged, that's whatever this foam, could be ice, whatever it is, times the volume of that. Well, if this portion goes in the water, that means if this tank was full, there's water coming off the side. What is the weight of the water coming out of the side? What should we call that? Fluid. The weight of the fluid that came out of the side is in that the mass of the fluid, which is rho of the fluid, times the volume of the fluid times gravity. Well, for something to float like this, that means these two forces must be equal to each other. So rho S times the volume of S times gravity equals rho of the fluid times the volume of the fluid times G. Since G on both sides, we can cancel that out. And I can tell you the volume of the fluid that came out is equal rho of the submerged over rho of the fluid times the volume of the submerged. I can tell you the relationship between the two volumes. Or rho of the submerged times the volume of the submerged equals rho of the fluid times the volume of the fluid. That's the same equation, by the way. It looks different, but it's the same equation for both. The fluid that came out is really the volume of the fluid is the same volume as submerged here. So that equation a lot of times is written because whatever goes in the water, that's how much water going to come out. The volume of the submerged equals rho S over rho of the fluid times the volume of the submerged. Vs. I should use S here actually for the solid instead of submerged. Is the solid actually the shape of this. That's the submerged. Can be submerged, submerged, solid, and submerged. So let's take an example. Let's say we got a piece of wood here floating in the river. This is the river. We got that piece of wood, the log. That's the log. This is the water. And the question is, what percent of, I don't know, the wood, the ice, whatever that thing you want it to be, above the level of water? Assume the density for that wood, W here, heavy wood, 917. Usually a wood is not that high. We'll say this is a heavy wood. Maybe it's coated with some tar, like telephone pole. And assume wood here. And the other one is water. Rho for water is equal to 1,000. The equation I'm going to use, the volume of the submerged, the portion that's going to be in the water, is rho for the solid shape over rho for the fluid times the volume of the solid shape. My solid shape made out of wood here, wood. So rho of the wood, the fluid is rho of the water, times the volume of the solid shape, which not given to me. So maybe I can find the submerged portion, the ratio to the solid. The portion of that submerged is going to be rho of wood, which is what? 917 over 1,000, which is 0.917. That tells me roughly 0.917 of that piece is going to be in water. 91.7% in the water. So how much above the water then? Above the water is going to be what? Isn't that 1 minus that number? Which is what? 8.3%? So 8.3% will be above the water. Okay, we'll stop here. One more section.